Okay, so as we were talking about earlier, you can't break atoms down or elements any further than their smallest part. This is kind of giving you an example. I kind of talked about it on the previous slide, but here's kind of giving you a real example. So imagine you have these iPods, and you can break them down further and further and further, but eventually you come down to one iPod, and you can't really break it down any further. Okay. So Dalton was a famous scientist, I believe in the 1800s, 18th century, so in the 1700s. And he kind of came up with a theory that explains atoms. This was really the first time. Now, they did talk about atoms back in like the Greeks and Romans, like Socrates and a few of those other philosophers. They did not believe in atoms. It just kind of shows you how smart they were. That's a joke. But they did not believe in atoms, and it really there were some philosophers that did, but like Socrates and Plato, they were the biggies, and pretty much whatever they said kind of was all believed. But after about 100 years later of them, or probably 1,000 years later, Dalton came out with his theory to actually kind of talk about atoms. That yes, there are atoms. A lot of these theories came about because how do you explain wind? All right, you can feel wind. Why can you feel wind? There's nothing there. If you have nothing, how can you feel nothing? Well, there must be something in the wind that you feel. Have you ever thought about that? Like, it's windy and you're like, well, I can feel the wind. Well, what is it? Well, it's all of the gas molecules quickly rushing by you and hitting you and against you and bouncing off of you. That's what wind is. Okay, and that's kind of what they thought about. Like, there must be something in the air that we can't see that is actually hitting us so that we can feel it. All right, so he came up with his theory, and I believe there are three statements. All right, number one is that matter is composed of tiny indivisible particles called atoms. This is kind of true. This part right here is not totally true. Okay, it's not really indivisible. Back then they thought it was, but 100 years after him, they started splitting the atom, and now it is indivisible. But it doesn't change. But back then, again, they weren't splitting the atom. Technically, a carbon atom is a carbon atom. You can't really change it anymore, for the most part. Again, chemically, you can't change it. Physically, physics, yes, I can split it all I want, but by chemistry, I can't change it. All right. Second statement is all atoms of a given element are identical. Okay, which also kind of is not true. Nowadays, we know about isotopes, which we will talk about. Isotopes. So this kind of isotopes are the same atom, but they differ in the number of neutrons. So sure, it's the same atom, but they technically are not identical. All right, they are identical in the number of protons, which we will talk about, and if it's a neutral atom, in the number of electrons. But we change neutrons to change the isotopes. But again, for a theory, this is a pretty good theory. All right. And then lastly, the third statement is atoms of one element are different from atoms of the other element. This is kind of the only statement that is exactly true. That means if I have a carbon atom and I have an oxygen atom, these are never the same. No matter what I do, they will never be identical. They are different. They will always be different from each other. And this was kind of a good theory because a lot of people were trying to make gold. We're trying to take lead and turn it into gold. And based on Dalton's theories, he's like, well, no, you can't. You either have a lead atom or you have a gold atom. All right, you will not be able to turn lead into gold. All right, so that's kind of what that theory came out of. Okay. So this kind of talks more about, so this was basically the atom. He didn't know about protons, neutrons, and electrons. Nowadays, however, we do know about protons, neutrons, and electrons, and those are called subatomic particles. So protons, neutrons, and electrons, these are subatomic particles. These are what atoms are now made of. These are even made out of things like quarks and leptons. I don't know if you've heard of those things, but these are made out of those things, which we don't talk about in this class. I don't even know much about them. Okay, so atoms technically are not indivisible. They are, okay, but they are made up of smaller subatomic particles. All right, the type, the number, the arrangement, all right, all determine the properties, which in turn determine the properties of everything we see, touch, smell, and taste. All right, so pretty much everything that we experience in our life is because of atoms. All right. The next few slides just kind of talk about charge, and they talk about basically how chemistry works and how things interact. All right. atoms have charge to them. They have electrical charge. They either have a positive charge or a negative charge. Some things have larger positive charges, some of them have larger negatives, or they have smaller negatives. It all changes in these types of charges. All right, and that's how atoms are attracted or are not attracted towards each other, is based off of these charge. All right, so opposite charges attract each other. Okay, that's how chemistry works. Something positive is attracted to something negative, and you form a bond. There are two types of bonds, which we will talk about in a different chapter, but just as a primer or an FYI, there are two types. One is called ionic, and the other one is called covalent, and we will talk about both of these in a different chapter, just kind of giving you a heads up. Opposite charges repel each other. All right, like charges repel, so two positives repel each other, two negatives repel each other. All right, and the more charge you have, if you have more charge, they repel even harder. Okay, so if you have a big positive and a big positive, they really repel each other. Opposed if you have like a tiny little positive to a tiny little positive, they're just kind of, yeah, okay, we just won't be attracted towards each other. Okay. And opposite charges cancel each other out. So this is kind of saying, yes, opposite charges are attracted to each other, but your overall charge of your molecule at the end should be a zero charge or a neutral charge. We don't really say a zero charge. We say it's neutral because in math, you say something is zero. In chemistry, we say it's neutral. Okay? So that takes us to kind of how the atom was kind of, or the like the model of the atom. The model of the atom. We knew there were atoms from Dalton in the 1700s, and then in the 1800s, people were like, okay, what do these atoms look like? And it really wasn't until the late 1800s, early 1900s, where we really started kind of trying to figure out what the atom looks like. So J.J. Thomson was kind of one of the first pioneers in this, and he kind of talked about this positive and negative charge in atoms. He was kind of the first one who figured out that there are these charges, the opposite charges are in an atom. You've got positive charges and you've got negative charges, okay? And he called them electrons. Those were the negative charges. All right, I don't believe he really talked about protons yet, which is the positive, but he knew the overall, no, so yes, he did have positive because he knew that overall the atom has a neutral charge. Okay, because he saw, so you can see here, Thomson reasoned that because all atoms appear to contain these negative particles, that there must have, and they were neutral, that there also must be some sort of positive charge in there. Okay, he proved the negative part of it, or the electron. He did not prove protons yet. It took another person to do that, but he reasoned since overall this had a zero charge, there had to be positive charges in there. And he said that these positive and negative charges were randomly all dispersed all throughout the atom, called it a plum pudding model. He was from England, and I guess plum pudding is very popular in England. Basically, it's, I think it's like a rice like pudding, and they always put raisins inside of it or nuts and things like that. And he was just kind of saying, so you've got this pudding, and you've got all the raisins and all the walnuts in there, and they represent the negative charges and the positive charges. And they were just randomly all dispersed all throughout the whole entire atom. Well, Rutherford won a Nobel Prize for his work in coming up with neutrons and the fact that you have a nucleus. He came up with the nucleus idea. Okay, and we'll talk about his experiment. So he refined the model by saying, well, you actually have a nucleus, okay, a very dense nucleus, all right, here's your nucleus, and then around it you have a lot of the space. And he figured out that the nucleus had the protons and neutrons in it. Okay, so you learn, I think like second or third grade about the atom, maybe third or fourth grade, that you have protons and neutrons in the nucleus, and he was the one who figured that out. Like everyone kind of learns that the first thing, and it was Rutherford that came up with the fact that you have protons and neutrons in here, and the electrons are all dispersed outside where all the volume is. Okay, so you have this dense core. all right, of positively charged protons and neutrally charged neutrons. That's why I put a 0 here, neutral charge, positive charge, and the electrons, which you do as a negative, was on the outside. Okay, just to kind of give you an idea of the size of an atom, I like to give a real-life example just so people can understand the size of the nucleus with respect to the volume of the electrons. Imagine you have a football field. All right, here's a football field. Here are the end zones. All right, 100 yards. Right, here's 10, 20, blah, 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 up to 100. So imagine a big stadium, a football field. Imagine the atom, the size of this football field. So imagine I have an atom the size of a football field. Okay, the nucleus would be the size of a marble right in the center. Oh, I don't want that. Right in the center of that football field. Just to kind of give you a visual, do you realize how dense that nucleus has to be? It's the size of a marble that's inside of this humongous atom. All right, and that's where the mass, all the mass, 99.9% of the mass is inside of that marble, where this huge, gigantic volume, 100 yards of spherical volume, have nothing but empty space. Well, it's not empty space. That's where the electrons are found. Okay, that kind of boggles the mind to kind of think about. Okay, so what did Rutherford do? He did this gold foil experiment, okay? And what he did, let me try to explain it, is he took gold foil, okay? Here is the gold foil right here, okay? Very, very thin piece of gold foil. And he had an alpha particle emitter, okay? Alpha particles, I believe, are helium atoms, all right? And he exposed the helium or the alpha particles to the gold foil. Most of these particles just kind of went through the foil, all right? You can kind of see most of the particles are going through the foil. However, every now and then he would get kind of a beam that would kind of ricochet off at an angle. All right, here it's going off at an angle, here it's going off backwards at an angle, and he had kind of this film, this screen, that kind of recorded where all the dots are going. You see here, occasionally one would hit here, one would hit there, but pretty much most of it would hit straight through, okay? So he was trying to explain these alpha particles being ricocheted off at angles. Why are some being hit off at angles? Most of them are going through. Okay, this is kind of the model of what he's trying to show. Okay, so let's actually use this one first. Okay, so here is one gold atom. Okay, so here's one gold atom. Here's the nucleus of the atom. These lines are the alpha particles. Okay, alpha, that's a Greek symbol for alpha. Most of these alpha particles are passing through in the huge volume of electron cloud. They're just passing through. Every now and then, though, one of the beams would hit this dense nucleus and just ricochet off. Okay, just kind of think of like if you play like billiards, and you take like the cue ball, and so I have a cue ball and I have another ball, and I hit the ball into this one. Okay, this ball will hit and then ricochet off at an angle. Okay, obviously if it misses the ball, it just keeps going straight. And that's kind of what he theorized. He was saying that the alpha particles are hitting our dense nucleus and are ricocheting off. A few of them would glance off right at the side and just kind of go off at another angle. But most of them would go straight through. So he reasoned, well, you must have tons of space, but there must be this small little dense center where every now and then a beam would hit it. Okay, and this is just kind of showing you gold foil with a bunch of atoms. Okay, here are a bunch of atoms. Okay, you know, a lot of times it like misses the atoms, but occasionally it will hit an atom and ricochet off. Okay, so based off of this gold foil experiment, Rutherford came up with the theory that you have a nucleus, very dense, most of your mass is in there, but most of your volume, huge portion of your volume, is in the volume of the atom. All right, and if you go on YouTube, you can, and if you do gold foil experiment, you can find people nowadays who are doing the experiment, and you can actually see how all the particles are going off on the screen, but most of them are going straight ahead. I mean, it's a really simple experiment. Okay, so what Rutherford finally came up with is you have nucleus, you've got protons and neutrons in the center, as he shows you right here. And then all scattered around, you have the electrons. Now, Rutherford said that all the electrons are randomly scattered around, but 50 years later, there were some scientists, you might have heard of one of them, his name was Einstein. There was also Schrödinger and Heisenberg. These guys, Heisenberg, not from the show. There was a show where one of the characters kind of nicknamed himself Heisenberg. There was a real scientist named Heisenberg that came up with the fact that these electrons are not random. They are not random, okay? They are in very specific energy levels. Okay, and when we get to the quantum chapter, we will talk more about how these electrons are arranged. Okay. Okay, so this is kind of a problem I kind of like that kind of starts talking about neutrons, protons, and electrons. Right? Remember, neutrons have a neutral charge, protons have a plus charge, electrons have a negative charge, and all depending on the amounts of each, you have an overall charge. Let me put here overall charge. Okay. So this should be pretty easy, okay? So if I have an atom that has 5 neutrons, 10 protons, and 5 electrons, what's my overall charge? Well, neutrons have a 0 charge. They have no charge at all, so I basically ignore that. So imagine I have 10 positives and 5 negatives, okay? I have 10 protons. So let me write here, 10 protons. 1, 2, 3, 4, 5, 6, 7, 8. 9, 10, and 5 negatives. 1, 2, 3, 4, 5. Well, that cancels, that cancels, that cancels, that cancels, that cancels. What do I have left? 5 positive. So my overall charge is a plus 5. Another way of writing it is a 5 plus. Okay, this is the more correct way because plus 5 implies mathematics. This has nothing to do with math. This is the charge on your atom, so it has a 5 plus charge. Neutrons have no effect on the charge whatsoever. It's how many protons versus how many electrons. Okay, so in the next example, I have 11 neutrons, 12 protons, 12 electrons. What's the overall charge? I'll give you a second to think about it. The answer should be 0, 0 charge, or a neutral charge. Okay, what about 8, 9, and 9? That should also be neutral. Okay, why? Remember, this has nothing to do with the charge. I'm basing 9 pluses versus 9 negatives. Okay, the last one, I have 21 positives and 20 negatives. So my overall charge is going to be a 1 plus. All right, hope that makes sense. And I will see you for the next videos.